3.1 determinants. So in this video, we're going to cover 3.1 and 3.2 together because they are rather short. So 3.1 determinants, we can think about determinants as a special number that is assigned to each square matrix. All right, so we're going to just quickly look at the definition. Right, so the definition is quite long for determinants. Basically, the definition tells you how to find the determinants, but I'm going to show you different ways of looking for determinants that is much easier and much faster. Okay, so you can take some time to look at the definition, but let's start by doing a quick review with just a simple 2x2 matrix, right? So A is a 2x2 matrix, then the determinant of A is simply, right, you multiply this way and then subtract that way, right? So the determinant for this matrix A would just be 1 times 4 minus 3 times 2, which gives you 4 minus 6, which is -2. Okay? Now, for a 2x2 matrix, it's pretty easy to find the determinant, right? But what about 3x3? What about 4x4s and so on? And of course, a lot of the computers now or programs now can calculate your determinant very fast without you doing any of the extra work. Okay, so let's look at theorem 1. Theorem 1 says the determinant of an n by n matrix A can be computed by cofactor expansion across any row or down any column. The expansion across the ith row using the cofactors in equation 1 is that. Okay, so I'm going to talk about what this is saying using example 1. So here we're going to look at example 1 using cofactor expansion method, which was discussed in the notes. Later I'll show you a different method, which is much easier and much faster. Okay, so what this is saying, first, that's a matrix A we're given. First, we want to find the determinant of A, and the determinant of A can be symboled using 2 bars, and then just fill in the numbers in here, okay, like that. Right. So what the cofactor expansion is saying is, first, we need to pick a row or a column. Ideally, you want to pick a row or column that has a 0 in it. Okay? So first, let's say I want to pick the second row right here. Okay. All right, so we can see that in the second row, we have 3 entries, 0, 3, and -3. Now, when looking for determinants, every entry has a sign of their own, right? It's not the sign of the numbers of the entries. It's the sign of the number that's in that spot, right? So the first one is going to be positive, right? And as you move right, left, up, or down, it's going to change signs, right? As we move to the right, it's going to be negative, positive, negative, positive, negative, positive, negative, and positive. Right, so you can see that the sign changes in every entry as you move left, right, or up, down. All right, so we're looking for these 3 values, 0, 3, and -3, right? So the entry right here is going to be negative. The entry right here is going to be positive. The entry right here is going to be negative. Now, it's actually a coincidence that the sign matches the sign of the entries, but notice that the signs in orange, they represent the signs of that spot, right? Whether it's a positive spot or in a negative spot, right? So to put this in use, right, we have to put these 3 numbers in first. So we have 0, 3, and -3. I'm going to leave some space in between, okay? And I'm going to add in the signs of those spots, right? So 0 at this space, so second row, first column, that's going to be negative, right? But negative doesn't affect 0. 0 is still 0. 3 is positive, that's plus. And at the spot, we have negative, so it's negative right here. Okay. Next, we need to finish our cofactor expansion. So after each one of these entries, you are going to be multiplying by a determinant of the cofactor, right? Of a smaller matrix, I should say. Okay. And we need to determine what these small matrices are. So first, what we're going to do is we're going to start with 0. So let's look at 0 in the matrix. 0 is right here. It's in the second row and first column, right? So I'm going to circle the first column as well. So second row, first column. Now, notice that these two circles, the red and purple circles, they cover a lot of the entries. And notice that there are 4 entries that we didn't cover, which is -2, 2, -4, and 7. And those 4 entries not covered by any of the circle is going to go into this cofactor, which is -2, 2, 3, oops, not 3, -4, and 7. Okay. All right. So same thing with 3. And then you just move along the row, right? We got 0. Now let's take care of 3. Right. So for 3, we are at second row, second column. So circle that second column right here. The 4 missing entries, 5, 2, 2, and 7. Right. Now, when we're looking for the cofactor matrix, we don't have to worry about the signs of the spot. Right. All right. Last, for -3. All right, there you go. And then that gives us a 5, -2, 2, -4. Okay. All right, so we have the setup ready. All right, so basically what we have here is we started by picking out the second row, and we take each entry, multiply by the determinant of the cofactor matrix, right? Which, again, remember how we got these matrix is by looking at the entries not being circled. All right, so let's do that. That's 0 times that's -14 plus 8. It's -6. All right, we actually don't care because 0 multiplied by this will give us 0. Plus 3 times 5 times 7, 35 minus 4, 31. And then that's a plus 3. Multiplied by -20 minus -4, that's -16. Right, so what do we have? We have 93 minus 48, which gives us 45. Okay, and then we can say that, okay, determinant of A is 45. Now, this is like by definition how you can find determinant of a 3x3, of a 4x4, or 5x5, and so on. Any square matrix, you can use this method to find the determinant. Now, imagine that if you're going to look for a determinant of 4x4, I'm going to give you a quick view, a quick idea of what we're looking at. All right, so we have a 4x4. All right, right, that's a lot of entries, right? And each one of them, if you select a row, you're going to have some number here, and then multiply the cofactor, and this will be a 3x3, right? Plus some another entry and a 3x3, and so on. And as you can see that by doing this cofactor expansion method, it's going to take you a long time to find the determinant of a 3x3 or a 4x4. Okay, so next I'm going to show you a really nice method that I learned, and it's going to save you a lot of time, and in my opinion it's much easier than this method, than the co-expansion method. 5, -2, 2, 0, 3, -3, 2, -4, 7. Okay, so this is what we have, a similar setup as before. We'll want to look for the determinant of this matrix A. All right, so I set up the determinant using the bars. Now here is something that I'm going to do different. I'm going to copy column 1 and column 2 to the right hand side, like this. All right, so I'm gonna copy down 502, -2, 3, -4, like that. Okay, and I'm going to show you this really sneaky way, maybe not sneaky, but a really fast way to find the determinants. Okay, so first we are going to look for products from the top down, top diagonal down. All right, so start with the first entry. All right, go down the diagonal. That's going to be your first number, second number, like that, and the third number, like that. Okay, so multiply all these three numbers to get first number, second, and third. And I'm also going to keep note. All three of them have positive signs. That means we just need to add them together. Okay. All right, so let's take care of the first three. So I have 5 times 3 times 7. That's 105. Plus, because it's positive, and then -2 times -3 times 2. So that's 612 plus 2 times 0 times -4, right? So we get a 0 here. That means the whole thing is 0. All right, that's the first half. And then the second half, instead of going from the top down in the diagonal, we're going to go from bottom up in diagonal. Right, so let me erase the orange circles first. Okay, like that. All right, and then we'll go from the bottom up in diagonal like that. Oops, it's really bad. Okay, 1, 2, and 3. Okay, and if you go from the bottom up, they are all going to be negative, means we are going to subtract these three numbers. All right, so first, subtract 2 times 3 times 2, that's 12. And then subtract -4, -3, and 5. So -4, -3, that's 12. 60 minus 60. And then subtract 0. Okay? No, 0. Right? And let's see what that gives us. So we have 105. So the 12 are gone. And that gives me 45. Hopefully the second method was much faster and easier. It's my personal favorite, right? That allows me to compute the determinant of a 3x3 matrix really fast. Okay? And it's faster than cofactor expansion because I actually time it myself. All right, for theorem 2, let's look at it together. If A is a triangular matrix, then determinant of A is the product of the entries of the main diagonal of A. Now, theorem 2 is very nice, very easy to use, and that actually will save you a lot of time when you're looking for the determinant of a matrix, right? So let's say matrix A is n by n, right? And then on the diagonal, I have A1, A2, A3, down to AN, and then a bunch of zeros down here, and then just some other numbers up here, right? The numbers up here doesn't have to be 0. So the important thing is all the entries below the diagonal are all zeros, right? Then theorem 2 says the determinant of A is the product of all the diagonal, A1 times A2 up to AN. Now, this is very nice, right? Because if you're given a 4x4 matrix, right, and then you can do elementary row operation and then bring it down to just a triangular matrix and then you can find the determinant basically by multiplying the diagonal, the entries on the diagonal, or the main diagonal of A. That is very fast, right? So to show you a quick example, right? So let's say I have a matrix B that looks like this: 1, 2, 3, 4, 0, 0, 0, 0, 0, 0, 9.5, -7/11, pi, e, apple, maybe not apple, but whatever, right? And 10. Okay, then the determinant of B is just 1 times 2 times 3 times 4, which is 24, right? By theorem 2. Okay. So theorem 2 is a really nice theorem. Keep that in mind when you're working on your homework, or whenever, if a question asks you to find the determinant of a matrix, this is one useful theorem to use. Okay, check if it's a triangular matrix. Right, it doesn't have to be upper triangular or lower triangular. Right. For example, if I have a matrix square matrix, and then instead of having the zeros below the diagonal, I have zeros above the diagonal. Right, this theorem works as well. Right. Right, it's going to theorem 2 is going to work on this matrix as well. Right, either the lower part is 0 or the upper part is 0. You can use theorem 2. Basically, multiply all the diagonals, multiply the entries on the main diagonals together, and you will get the determinant. Okay, 3.2 properties of determinant. Bring up the notes if you don't have it yet. So theorem 3. Let A be a square matrix, and then we have 3 items. Theorem 3. Let A be a bi-n matrix. So the 3 points under theorem 3, they are talking about the elementary row operation and what that does to the determinant. Okay. So for example, first, if a multiple of one row A is added to another row to produce a matrix B, then determinant of A is equal to determinant of B. All right, so I'm going to show you what that's talking about. So let's say A is 1, 2, 3, 4, and then to get B, I'm going to say row 1 is going to become 2 times row 2 plus row 1. All right, and then I get another matrix that looks like 2 times row 2, so 6 plus 1, 7, 2 times 4, 8 plus 10, right? And then I'm gonna call this matrix B, right? And what this is saying is this is one of the elementary row operation that we use a lot when we want to reduce the matrix down to a reduced row echelon form, right? So this elementary row operation keeps the determinant, right? Does not change the determinant. Okay, so determinant of A is going to be the same as determinant of B, and let's check that real fast. Right. So determinant of A is 1 times 4 minus 3 times 2, which is -2. Right. And let's see, determinant of B is 7 times 4 minus 3 times 10, and that also gives you -2. Okay, easy, right? Okay, so that's the first one, does not change the determinant. And let's look at the second one. If 2 rows of A are interchanged to produce B, then determinant of B is equal to the opposite of determinant of A. All right, so if you interchange rows, determinant is going to be opposite. All right, so 2. Let's say A is, again, 1, 2, 3, 4. And then we interchange row 1 and row 2 to get B, 3, 4, 1, 2. Then we know that from earlier determinant of A is -2. And by this theorem, what do you think determinant of B is going to be? Right? Let's check. 3 times 2, 6, minus 1 times 4, 4, which gives you +2, right? Notice that determinant of A and determinant of B, they are opposite of each other, right? So determinant of A is equal to the opposite of determinant of B. Or you can do it the other way, right? Determinant of B is the opposite of determinant of A. Okay, that's the second one. All right, and the third one is when you multiply a row by a constant. Right? So let's say A is 1, 2, 3, and 4. And then I want to get matrix B by multiplying row 1 by -1. Let's not do -1. Let's say -3. Right. So row 1 is going to become -3 row 1. That means row 1 is going to be -3, -6, and row 2 is still the same. Right. Let's call that matrix B. And again, we know that the determinant of A is -2. And let's check determinant of B. Right. -3 times 4, -12, minus 3 times -6, which is -18. That gives us +6. Okay. -2, +6. And we did that by multiplying row 1 by -3. Okay, so what this does is if you multiply a row by a constant, the determinant is going to change by doing the same thing, right? Determinant is going to change by multiplying by the same number, right? So -2 times -3 gives you 6, right? So in this case, determinant of B is going to be the constant K multiplied by the determinant of A, where this constant K is the number that you multiply some row by. Okay, so that's the 3 elementary row operation, right? The first one, when you multiply and add, it does not change the determinant. The second one is when you interchange rows, you get opposite determinants. And the last one, when you multiply a row by some constant K, the determinant also gets multiplied by that constant K. All right, theorem 4 is very nice, right? It's so good, so important. I'm going to write it down. And n by n matrix A is invertible. Right? Remember, invertible, that means the inverse of A exists. And n by n is invertible if and only if the determinant of A is non-zero. Okay, so this works both ways. I'm going to talk about this for a little bit. All right, so if you know that a matrix A is invertible, meaning you can find its inverse, then we know for sure that the determinant of A is non-zero. Vice versa, if you want to check if a matrix is invertible or not, you can do that by looking for the determinant. If the determinant is not 0, it means the matrix is invertible. If the determinant of the matrix is equal to 0, that means inverse of A does not exist. That means you cannot find the inverse of A. Theorem 5, determinant of the transpose of A is equal to the determinant of A. So nothing to say here. It's pretty straightforward, right? If you don't know what transpose is, basically the rows becomes the columns becomes the rows. That's how you find the transpose. Right? To show you this, you can look at a really simple example, 1, 2, 3, 4. All right, we know determinant of A is -2, right? And the transpose of A will be 1, 2, 3, 4, like that. And let's check the determinant of the transpose of A. 1 times 4 minus 2 times 3. Okay, boom, done. Right, they are the same. All right, theorem 6. Suppose we have two matrices, two n by n matrices A and B. The determinant of the matrix A times B, right? A times B is going to be some matrix, right? Is equal to the determinant of A multiplied by the determinant of B, right? So pretty straightforward. Not going to take time to prove this, but I do want to spend some time showing you how to do example 1. All right, so example 1, we are going to be applying theorem 3 to find the determinant of this matrix. Now, of course, you can use the method that I showed you guys earlier, or any other method to find the determinant, but I want to show you how to apply theorem 3. So I'm going to ask you guys to try to perform elementary row operation on this matrix to get to reduced row echelon form, and I'll do that in a second. Okay, here I have all the steps written out to reduce the original matrix down to a reduced row echelon form. So to find the matrix of the original, we are actually going to go backwards, right? We're going to go from the reduced row echelon form back to our original matrix. The reason why is because it's easy to find this determinant, right? So I'm going to make a note. The determinant of this is equal to, let's call that A, right? A prime, right? We're going to go back to A, right? So it's just the diagonal, right? 1 times 1 times 1, which is 1. So going backwards, we're going to look at our elementary row operation and see what that does to our determinant, right? So going back first, this elementary row operation is when you multiply a row and adding to another row. Now, hopefully you have the notes next to you. That's theorem 3.1, right? If a multiple of one row of A is added to another row to produce a matrix B, then the determinants are the same. It means the determinant of this matrix and this matrix, they are the same, right? So I'm going to make a note. It's 1 up here, right? Or maybe I can just do this. That's equal to 1. Right, equal to 1. All right, now let's go back further, right, to this one, right? Notice that the elementary row operation here, they are still the same thing, right? Taking multiple of some row, adding to another row for both of them, right? That means the determinant is still the same, 1. And another way that you can look at this is that's a triangular matrix, right? So determinant is still going to be 1. All right, moving back another one, right? Still taking a multiple, adding to another row means determinant does not change, still 1. All right, going back further, now this is the one where we're going to have some sort of change in our determinant. Okay, so to go from here to here, we multiply the second row by -18 to get here, right? So what's the opposite of multiplying by -1/18? It's dividing by -1/18, right? So the determinant here, it's going to be 1 divided by -1/18, which is -18. Okay. All right. Now go back one more. They are still just multiplying a row, adding to another row means determinant does not change. But determinant here, it's -18. So back to the original, we get determinant is -18. Right. So let's look at what we're doing here again. Right. So going back, we started with at the end with a reduced row echelon form. So this doesn't change determinant. All right. This doesn't change either. Doesn't change. All right. This part doesn't change it either. No change. And this part is going to change the determinant, right? So maybe this is a little confusing. To go from here to here, to go in this direction, we have to multiply the determinant by -1/18. So we're going the other way. We want to go in this direction. Means we're going to do the opposite of multiply by -18, which is divide by -1/18. Okay. All right, and then of course back into here, it still does not change the determinant. All right, no change. Okay, so let's check if the determinant of the original matrix is actually -18. Right? I'm going to use the method I like, the second method, to show you how we can find the determinant of a 3x3 real fast. Okay, so imagine that you have column 1 and column 2 to the right, and then you multiply top down 3 times and bottom up 3 times. So top down, we have to do adding, and bottom up, we have to do subtract. Okay, so 1 times -3 times -7, 21. 5 times 3 times 2, that's 30, plus 30. -3 times 3 times 13, that's 9, 27, so -117. Is that right? Yep. Okay, now bottom up, 2 times -3 times -3, that's -18. And then -39, right? 13 times 3 times 1, and plus 105, right? -7 times 3 times 5, right? So what do we have? We have 156 minus 174. Is that right? Yep. Which is -18. Check. Right? So you might ask, okay, this is definitely much longer than this method, right? The method that we just did. But this helps us to understand what elementary row operation does to the determinant, right? What changes does it make? And sometimes, we can use this to determine, okay, let's say there's a specific determinant that I want to hit. What elementary row operation can I perform to get to the result? Okay, but that's basically it for 3.1 and 3.2. They are fairly short. Be sure to look at the homework, and that'll be it. I don't know if you guys have seen my announcement on Blackboard, but I do have office hour every Tuesday and Thursday from 1 to 3 p.m. All right, hopefully I'll see you guys there, and have a good day.